Hi, I'm Melanie, and I work at Microsoft. I'm a Postgres developer and committer. And today I'm going to talk about feedback-directed optimizations. And throughout the past couple years, I've done a few projects trying to add different types of adaptive algorithms into Postgres and various subsystems. And I wanted to kind of talk about what I learned and how I failed, and hopefully we can succeed together. I don't know. So in Postgres, we have many optimizations that are meant to offset the negative performance consequences of different operations that are required, like garbage collection by vacuum or things like large bulk operations. We use things like buffer access strategies. We have the vacuum cost delay system. We have background writer throttling, wall writer throttling. And a lot of them use either GUCs that have static, that are a form of static configuration, or heuristics that don't change. And so if you think about, for example, copy uses a fixed size ring buffer. So if you're doing, a big data load, you might not want to wash out all the rest of shared buffers. So we use a ring buffer to avoid doing that. But the ring buffer is a fixed size, right? So it doesn't really respond to, okay, how many of your shared buffers are you actually even using? Or, what is the what is your usage pattern? And there's a lot of opportunities throughout the system. And actually, I wrote this proposal, obviously, before I wrote the talk. And I went through and looked, and I was like, actually, we have a lot of small, sort of confined optimizations that are a little bit adaptive. So I was actually a little bit wrong. We do have some things. But why do you want something that's not just static configuration? Well, if you imagine a typical system, it's not going to go the same TPS all day. Well, some may, but unlike PGConf will lead you to believe. But there might be different times of day that are busier. People are buying things in the afternoon when they're falling asleep at their desk on your app. So having the same algorithm for a prefetcher in a system when it's the most busy or it's the least busy doesn't necessarily make sense. And there are also diverse access patterns. So there are tables, like if you imagine an insert-only audit table versus a hotly updated table, there is something we can know, there's something knowable about when the data will go cold in an insert-only table. It'll be accessed for a little bit, and then it won't be needed anymore. And so you could hypothetically do something based on that information. Or, if you think about our eviction algorithm, it's not we don't know anything about which buffers have which blocks, and if those belong to an index or those belong to a kind of table that's going to be insert only or that kind of thing. So I'm sure there are some databases that do things like don't kick the top few levels of a B tree index out of shared buffers, even if the eviction algorithm would normally tell you to do so. And yeah, I threw this in after David DeWitt's talk yesterday. There's databases that do adaptive query optimization. So I think the idea of, adapting based on the mistakes that you've made in the past. So you plan a query, then it doesn't go so well during execution, and so for that same query, maybe you don't plan the same plan again, or during the execution, you switch out to a different plan. I'm going to talk mostly about these kinds of algorithms in the context of applied to vacuum, but I just wanted to give some more examples across different domains or subsystems to start out with. And so what do I mean by adaptive? I think any sort of mechanism that changes behavior based on data collected at runtime. And the two categories that I think about are changing based on system state, so how much I/O you're using, what's going on in the system, and then changing based on past behavior, so attempted tunings, things that you tried to do to the system and they didn't work, and so you adapt based on that. The two classes of adaptive algorithms that I'm going to discuss are feedback controllers and predictive inference. So feedback controllers are often used in industrial settings or industrial systems, and basically it just is you have some way of measuring what's going on in the system at a given time, and then you have a desired system state, and you make changes to the system configuration in response to the output saying what's going on, and try to drive the system to that desired state. And an example of this is like cruise control in a car. So it tries to, it might go one way or the other and then try to drive you towards the speed that you set in the cruise control. Here for predictive inference, what I'm talking about is basically any gathering data about, you come up with some hypothesis and you gather data, and then based on that data and some empirical model that you devise, then you try to use that to make predictions about how you should tune a system. So like you have to make some assumption that past behavior can predict future behavior for that to be useful, but yeah. So I am gonna walk through examples, in both cases, different parts of vacuum. And so recently, this was like a month ago, I tried to do a feedback controller patch for doing dead tuple cleanup or addressing bloat in vacuum, and very experimental, hacky prototype, but I just wanted to walk through the thought sort of questions that I asked and what I learned from that. And then for predictive inference, the example that I'll talk about is over the past few years work I've done to try to preemptively freeze tuples. So first I'll talk about the feedback controller, and it's an attempt to pace an ongoing auto vacuum with that feedback control type thing I was talking about. So a few years ago, I was working on trying to come up with a prefetch algorithm for the AIO project that Andres Freund talked about earlier today. And I had the idea to use a PID controller to do that kind of prefetching. And I worked on it for a long time and nothing came of it. And recently, Thomas Monroe has picked up the mantle and is trying to do something with that. So it's a really interesting idea, and I think I kind of got stumped at the end, and I thought, well, this is an opportunity to take this kind of approach and apply it to a different subsystem. So I wanted to try to use it with vacuum. So what am I even talking about? Vacuum has to clean up dead tuples, that's its main job. And so when you do updates and deletes, there's old row versions that are left behind. And as time goes on, if you don't do anything, your useful data will be spread out across more and more pages, and then your performance will go down because you have to read in more and more data to actually satisfy your queries. So we want to clean up the old row versions and make space for newly inserted tuples to be added there. And we want to do this in a way that doesn't disrupt foreground workloads. You can imagine that if you waited and did it all at one time, then that might be pretty disruptive to ongoing queries. How do we do this now? Well, currently in Postgres for pacing vacuum, we use what's called the cost-based vacuum delay system. So how it basically works is a vacuum worker, we assign costs to different operations like a page miss or a read or whatever, and then once you add up those costs, and once a threshold is hit, the worker will sleep for some amount of time, wake up, and repeat. And that means that vacuum ends up removing tuples at an effective rate that's slower than the maximum possible rate that it could go. And what it doesn't consider is how much work is remaining, how far behind you're falling. And as I was mentioning, as you're creating more and more bloat and more sort of cruft, it's going to affect your system performance. So there's a cost. Yes, there's a cost of vacuuming. It can disrupt foreground workloads. But there's also a cost of not vacuuming. And it doesn't consider that. It also doesn't consider things like slack in the system. So there's a presentation that Robert Haas gave last year at PGConf.dev about problems with auto vacuum, and most of the way that I thought about this problem is really based on things he talks about there and discussions that we have had and I and other people have had about what vacuum's responsibilities and purpose is. So the idea behind this like prototype and project that I was doing was to try to pace vacuum based on the amount of work that there is to do. And so in many of the discussions in the past few years about this, one of the approaches that people have brought up is the concept of a deadline. So first, like I said, you have all these dead tuples and they create bloat, and you need to remove them in order to be able to free up space to put new tuples. So if you think about across all your tables in your whole database, all of that dead stuff, that's like your backlog. You have to pay that down in order to make the system be in this desired state. So one of the things that has been discussed is coming up with basically calculating for a given table, the portion of the global backlog that it represents, then the dead tuple generation rate for that table, so how quickly are you doing updates and deletes, like how many new dead tuples are being generated, and then we would also need something around the XID consumption rate for that table. I'm gonna set that aside for this because I didn't include that in my prototype. And then using all of that, maybe you could come up with a deadline, and if a given vacuum would have to finish by that deadline. And I think it's like pretty abstract to talk about it, so I want to give a specific example. So imagine a database with a single table, with a single auto vacuum worker that's vacuuming the table 100% of the time. Obviously this is like, but it's just a thought experiment, right? So now that table has 1 million dead tuples. We're starting a vacuum, there's 1 million dead tuples, and let's say that we're fine with 1 million dead tuples. That's the amount of bloat that we can tolerate. All we want is that by the time we finish this vacuum, the current vacuum that we're starting, even though there are new dead tuples being generated, the number of tuples in the backlog stays, the dead tuples in the backlog stays at 1 million. So in this example, we have new dead tuples being generated at 1,000 dead tuples a second. Side note, these numbers are probably, like, they're just to be most easy to understand the math. So the next vacuum would have to basically finish, so this current vacuum would have to finish in 1,000 seconds such that there was 1 million dead tuples in the backlog when it finished. Okay. There's gonna be a few numbers, so tell me if it doesn't make sense. Okay, so doing that, we would need to match the dead tuple generation rate with a removal rate of 1,000 tuples removed a second. And you would have to go faster if you wanted, the backlog to be paid down. And now rate sounds fine, but there's lots of ways that we could do, like there's lots of ways that we could implement actually keeping vacuum working at an effective rate that is lower than its maximum effective rate. But I think the easiest way to think about it is if we use the current system, which I'm not saying we should, but of sleeping and delaying like that, then you could achieve a certain rate by saying, okay, after every page, I'll delay for X amount of time, and that's how I'll achieve the effective rate. So still use the vacuum delay, that thing that we have now. And to calculate the delay, you would also need to know, so the 1 tuple per millisecond removal rate is what's the previous slide we determined that we needed. So we have that. Then we need to know how much, like what portion of the backlog we're removing basically per page. So in this case, for this example, I'm saying there's roughly 40 dead tuples per page. So this gives us a 40 millisecond delay per page. Wait, did I do that right? Okay. Right, so we need to, wait, this is backwards. Oh, okay, so but now our system is probably not going to delete and update tuples at a consistent rate forever, at the same rate, 1,000 dead tuples a second. It's very likely that the rate will change. So we developed the deadline based on the idea that there would be 1,000 dead tuples a second being generated. But so let's say halfway through we suddenly have 2,000 dead tuples a second. Well, at that point, we need to change the delay and match the increased dead tuple rate. So at that point, we would decrease our delay for the remaining pages to 20 milliseconds a page. Now, at the beginning, I said, okay, we have a backlog of 1 million tuples, And at the beginning of vacuum, we set like a visibility horizon. So those 1 million tuples, dead tuples, are the only dead tuples that this vacuum will be able to remove. All the incoming dead tuples that I said 1,000 dead tuples a second, this vacuum will not be able to remove those tuples. However, we need to finish this vacuum in time to start the next vacuum to be able to remove those dead tuples. So let's say that we're doing this vacuum and we have a long-running transaction. And that means that we thought we would be able to remove those 1 million dead tuples in our backlog, but actually we can't. We can't remove very many of them at all. And what that halfway through, let's say we still have 800,000 instead of 500,000 dead tuples. So assuming that we can't change our deadline because we need to finish this vacuum before the next vacuum would need to start, we could speed up in order to accommodate that. And we could say, well, we thought we were going to move 500,000. We didn't. We only removed 200,000. Let's go faster for the remainder of the vacuum. And if you combine this kind of, your dead tuples are not going to be uniformly distributed across all your pages, or if they are, that's super cool. You managed to do that. But you are likely to have both things. You are likely to have both changes in your incoming dead tuple rate and changes in or variation in the amount of the backlog that you are able to pay down at a given time. So you would combine these to come up with the actual rate that you are trying to achieve. And when I implemented this, the way that worked the best, or the way to think about it, was basically like, even though all the new dead tuples can't be removed by this vacuum, I'm going to take those 1 million dead tuples I had, that's my starting backlog, and then all the new incoming dead tuples are counted in that same cumulative backlog. So, I'm not going to be able to remove those this vacuum, but I'm still going to include those when I'm calculating the current speed, and then divide that by the time remaining and convert that to a delay. And what happens as we have these variations and you're unable to finish the current vacuum, or you're unable to remove all the tuples before the next vacuum has to start, is that you'll start to speed up and speed up and speed up, and obviously you can't go infinitely fast, so eventually the delay will be 0. And I think one of the things that this system would probably do is just always end up with a delay of 0. So it doesn't seem great. I see Robert's face over there. But I think another another thing that is even originally I started out and I was like, we have a single table in a database being continuously vacuumed, and that's obviously not a real situation, right? So you are going to have many tables. They're going to be system resource constraints, multiple vacuum workers. So actually calculating a deadline that's accurate is going to be pretty hard. So instead of doing that, I think deriving the deadline is going to be too hard, so I moved towards a system that was a little bit more flexible. So the way that I started thinking about it is, if you have a really big table, you don't want to spend the same amount of time vacuuming each page of a big table as you do vacuuming each page of a small table. If you did that, then you want to basically, if you have only small tables, you want to spread out the work that the vacuum workers are doing and spend more time not working in between. So when you have a lot of work to do, the delays will be smaller and your rate will be faster. And when you have little work to do, you'll delay longer. And that relationship is basically proportional. And we don't necessarily want it to be completely proportional because, for example, there's probably no table that you want to take 5 weeks to vacuum. But there's sort of a roughly proportional relationship there, which is just the rate would be some constant. In a controller lingo, it's gain, we call it gain, times the size of the cumulative backlog that I mentioned earlier. And the other thing the other property of this is a linear relationship between the backlog and the removal rate. So when the backlog is twice as big, you want the rate to be twice as fast. And I don't know that the correct relationship is necessarily linear, but the way that I thought about it was driving a car. So if you're trying to go from 0 to 70, you're going to depress the pedal more to get up to speed than if you're trying to go from 60 to 65, because you want to try to get up to speed quickly, but it's okay. You don't care so much how quickly you get from 60 to 65, and it's actually worse if you blow past 65 to 100, right? But if you're driving a car and you're drifting into the next lane, if you're drifting a little bit, you can, do a correction that, like, however long it takes you is probably not a big deal. You probably won't get into a car accident. But if you're 1 foot or 2 feet into the next lane, you need to be like turning the wheel a lot to get out of that lane. So it doesn't seem to me like dead tuple cleanup that there's a point where it becomes absolutely catastrophic and we need to completely change the rate suddenly in a relationship that is super linear. But maybe I'm wrong. Okay, so I wrote a patch that does this very hackily. There is like a small GitHub link there. I do not recommend going there, but it has a bunch of fprintfs to put stuff out to a CSV so I could like make all these charts and stuff. Anyway, so the test case that I used was I insert and delete. So I started with a table that had some data in it, and then insert and delete the same number of rows. So insert 20, delete 20, insert 20, delete 20. And then at the beginning where that flat line is, I'm sleeping for longer between each of these inserts and deletes. And then as that line is the dead rate. And then as it goes up, I'm sleeping for less time, so the rate of dead tuples being generated is higher. And so I do that back and forth a few times. And that's the same image at the top, and this is the dead tuple backlog. So the orange is with the linear controller I mentioned, and the blue is master, and it's doing a slightly better job of keeping the backlog down. And this is the delay. So this is how it changes the delay in response to the changes in the dead tuple rate. I think one of the issues that I had was it was hard for me to we do not expect the backlog of dead tuples to be 0. It would be far too aggressive to try to keep the backlog at 0, right? So you need to have some evaluation criteria to say what, for a system like this, you need to drive to a desired state. And at first I thought that desired state is some constant number larger than 0 dead tuples. But I'm not so sure after experimenting with this that that's true. And so I tried a lot of other things, and I made a lot of charts and captured a lot of data. And the thing that sounded the second best to me was, so if you have a constant amount of data that's live, like, you're inserting and deleting the same number of tuples, but the data that's actually there that's alive is the same, then the file size should be the same. Like if you actually look at the file in the file system, because you should be reusing all the free space that vacuum frees up. And so I tried that as well, and plotted that and tried to drive that to the ratio between inserted data and the file size to make those converge. And that also didn't work. And so I don't really know what would work, but I think that I found that this project, I didn't want to go any further for a few reasons, and one of them was that I didn't feel like I had evaluation criteria that made sense. There was another couple, I'm definitely not going to work on this, basically, because it's super hard. And obviously, initially, when we're talking about doing this for a single table, that won't work, because what if you have a table that is not bloated at all, so you vacuum it super slowly, and meanwhile the rest of the system has tables that need vacuuming, so without scheduling or prioritization, that wouldn't, maybe it would work, but I couldn't think of a way. But actually the thing that scared me more was, so vacuum has 3 phases. The first phase is we go through and we can basically set line pointers so that later we can come and clean up the tuples. And the second phase is index vacuuming. And the third phase, we can actually remove tuples. So there are exceptions, it's complicated, but we don't really remove, we don't make free space up that much in the first phase. So all of my sort of these rates and making everything balance out was based on the idea that I was incrementing and incrementing the remove tuple counter in the first phase, which means that it didn't account for the fact that there's work to do in the third phase. And then in the third phase, I couldn't calculate a delay at all. And maybe there's something cool you can do there, but it's just felt like a fundamental problem. Like I had that spidey sense bad feeling. The other thing is that, so on-access pruning can set line pointers to be dead. And that means that in vacuum, you can have pages that need to be read in because they're not all visible, but there's no or little less phase 1 work to do. Most of the work is in phase 3. So calculating the rate, given that it's unclear which of phase 1 and phase 3 the work is going to be done in, also seemed very hard. And then I just set the delay to be like a really small number during index vacuuming. I just sort of was like, index vacuuming, pacing, I'll figure later. But yeah, maybe it would be sufficient to just have a constant, because you have to read the whole index, so maybe just factor that in. But I sort of wonder if it's not more complicated, because then for the index entries that you actually delete, you do have to do wall, so like that costs something. Anyway, it just got complicated and scary. So then there's like taking a step back, which I'm not usually good at, but like, is this even the right approach at all? This is one of the crosses I bear, is that I have a hard time with this taking a step back thing. So a lot of, I think the biggest question is like, this system does more work when the system is more active. So I think it's not a good idea to just wait until the system's not active at all and do all your vacuuming then, but like having a system that's completely optimized to do the most work when the system is most active might not be the solution. I think you could do the controller model with something other than vacuum delay to do the pacing, but like what you actually choose for that might fundamentally affect the design. So I'm not so sure that you should just say, I'll figure that out later kind of thing. Okay. What am I doing on time? So what about XID wraparound? So I only talked about dead tuple cleanup, and there is more to vacuum's list of responsibilities. So when I mentioned this to Andres, he was like, oh, maybe you can just insert it instead of the dead tuple insertion or dead tuple rate, you do inserted tuple rate, and then instead of removal, it's freezing. But I feel like there's something a little bit different here, because an inserted tuple isn't a danger unless it's unfrozen. And when you remove a tuple, there's space freed up, right? When you freeze a tuple, it doesn't free up any space. So the evaluation criteria would have to be very different, I think, for this. And then once you have totally different evaluation criteria for a system, I feel like it's likely that other things about the solution change. Yeah, okay. Anyway. But on the topic of freezing, I did spend a large number of hours over the past few years trying to figure out how to predictively freeze tuples. And so what is freezing? Because Postgres has 32-bit transaction IDs, a lot of people use more than 4 billion transactions in the lifetime of their database. So once the wraparound happens and you have a tuple that hasn't been frozen, it will appear as though it was inserted in the future and then become invisible. So once a tuple is visible to everyone, we go and need to basically flip a bit on it to indicate that, so no one tries to use the inserting transaction ID to determine if it's visible anymore. This is primarily done by vacuum. There are exceptions right now, but primarily done by vacuum. So knowing that we have to freeze data at some point within our current system, when do you do it? You could wait until you're pretty close to running out of transaction IDs and then go and scan and read in and freeze all of the unfrozen data. But that can be a lot of data. So we don't do that. And once you run out of transaction IDs, you can't have any more until you've frozen the data that's in danger. And so then your system becomes read-only. So what we do in Postgres is we have a few gucks, and basically after 50, so vacuum is main responsibility, like I said, is dealing with bloat. So when normally in a normal vacuum, it's only going to read pages that are not all visible. So pages that have work to do on them for it in its bloat reduction goals. Though if any of those tuples are older than 50 million transactions by default, then we'll freeze them. But normal vacuums are not going to scan. It's very likely that you have data that you inserted and haven't updated recently and therefore don't need to vacuum that is unfrozen. So about every 200 million transactions, we do what's called an aggressive vacuum. We scan all of the unfrozen data and then freeze any of the tuples older than 50 million at that point. So like looking at this timeline, which is probably not to scale, but the 200 million is definitely a lot less than 4 billion, right? So it seems like, hey, that's probably gonna be good enough. But the thing is, like, you could do a bulk copy and have terabytes of data that all has the same transaction ID. So it actually is quite possible to have enough data by 200 million transactions that it's pretty disruptive to your system. And so looking at the gucks, the gucks I just discussed, you can actually set per table, and that's a good way to, within the current system, to be able to accommodate different access patterns. But by default, it's the same regardless of whether you have an insert-only audit table or a hotly updated table. And it seems like, we could gather some information throughout the lifetime of the table, save it, and then use that to determine when we should freeze data, because we should probably freeze data sooner for an insert-only table than for a hotly updated table. So one of the early sort of efforts that I made here was so each page has a log sequence number, an LSN, and because that number is like monotonically increasing, you can do things to kind of make it approximate time. Just believe me when I say that, and we won't get into the details of how to do that. And so the idea was to make a distribution of the unmodified durations of pages. So then for that table, so this is per table, when I'm vacuuming a page, I look at how long it's been unmodified and say, is it in the older portion of pages for this table? Like pages in this table are normally modified after 5 minutes and it hasn't been modified in 5 days, so it's in the oldest portion of the table. And this is based on the idea that a lot of the time, or for a lot of data, it's going to be updated for a while, inserted, updated for a while, and then eventually it will quiesce, stop being, become cold, and then it won't need to be in shared buffers anymore, it'll get evicted. And the longer that you wait to freeze a page, the more likely it is to have passed this quiescence point, and then what happens is so imagine that page is on disk, you have to read it in, and it doesn't have any vacuuming work to do on it. You have to read it in, then you dirty the page again, so you have a read, a write, and you have to omit wall. So yeah, you dirty the page, and then because you have to omit wall, and then you're using a limited number of buffers, so you end up having to actually write the page out so you can reuse that buffer for another of these cold blocks that you sadly are out on your SSD. So that means that there's write amplification that happens when you don't freeze pages with enough, when they're still sort of, before they're evicted or, out, quiesced, before they've quiesced. So Robert and Andres and I spent like many hours of our life talking about different ways to kind of approach this problem and how to think about it. And so this line, the blue line, is the last point. Orange, like red is hot and orange is less hot. I think that maybe that's clear, yeah. Is the last time the page is modified, and then it's not modified again anymore after it's gray. So when do we want to freeze it? We want to freeze it when it's not going to be modified again, the last time that it's vacuumed, and when it's not going to be modified again, so that we don't have to like once it's modified, then we're going to have to freeze that tuple again. But this is actually asking the question, is this the last time the page will be vacuumed, which is pretty much too hard to answer. We had a distribution of the unmodified durations of pages. And if you wanted to predict or tell the probability that a page, it's the last time a page was vacuumed, oldness is not a proxy for that, really. It kind of sounds like it might be, and maybe it is in a lot of cases, but you would need to know the ages of pages at the time they were last modified. And fundamentally, like, if you're gonna die tomorrow, you don't know this is the last breakfast you're ever gonna eat, right? Like, so it's hard to know if it's the last time it's going to be vacuumed. Yeah, seize the day. So all of the existing GUCs are kind of structured around the idea that we should freeze old stuff. But actually, like, this was sort of the turning point, I think, in the project, one of the two turning points. And Robert was like, we should rethink of it. It's not about how can I only ever have frozen this page once, you know? If that was the case, then you would just do the aggressive vacuum, right? So what you actually want to know is how often can you tolerate useless freezing? So if you vacuum a table that's like all the pages are getting updated, you're vacuuming it every minute or every 5 minutes, then it would be pretty bad if every single time that happened, you froze every single page in that table every single time, right? But if you're vacuuming a table every day or every 2 days, if that's the usual cadence that it's being vacuumed, then having some pages get frozen that later, 1 or 2 of the tuples on the page are unfrozen or modified, and the page is unfrozen, might be okay and a decent price to pay for not having your system go read-only, or an aggressive vacuum be disrupted to your foreground workloads. So the question changes to, is the page old enough to justify freezing it, to is it young enough to stay unmodified for some amount of time? And Robert came up with the idea of target freeze duration as a term. And basically, we said, are you willing, like, how often are you willing to have useless freezing? Well, that translates to how long should, what is the minimum amount of time a page should stay frozen for you to be happy or that you can tolerate? So going back to our distribution, basically the same distribution we had before of unmodified page durations, or unmodified durations of pages. If you look at the purple, that's, instead of a frequency distribution, now it's a probability distribution. And all the purple is the probability that a given page will be unmodified for more than an hour. And taking our target freeze duration back in, that this is the probability, the orange is the probability that a given page will be unmodified for more than an hour and 40 minutes. And here we made our target freeze duration 40 minutes. So that seems pretty cool. And when we're vacuuming, maybe we can just use that. But the actual probability that a specific page is going to stay unmodified is slightly different than that, because we know the age of the page, like that we have that information. So we know that the probability that the page will be unmodified for less than an hour is 0, because it's already achieved that. So the probability that it will stay unmodified for more than an hour and 40 minutes is actually the probability that it will stay unmodified for more than an hour and 40 minutes divided by 1 hour. This picture is more clear than I could explain it. But it's essentially like if you chopped off all of this, because all of this is impossible, and it just this, right? So anyway, this seemed cool. And the nice thing about it is that for tables where all the page, we don't need to do any freezing, hopefully what this allows us to do is not freeze, because the target freeze duration will always be longer than the younger pages that are being constantly updated. And so I had a branch, this is a Okay, so this is some results for a branch that I had for a hot tail type workload where you're inserting data, then you're updating it a bit, and then it goes cold. So just the end of it's being updated. And what's on the bottom is what I said earlier is the all visible but not all frozen pages. That's your debt. You have to pay that at some point. You have to freeze that data. And so if you build up enough debt and the aggressive vacuum has to pay that all down at once, you're going to see latency in your system for foreground workloads. It's going to affect things in your system. So what you want is a smoother line for your all visible but not all frozen debt. And on the top is the actual page freezes. So pages being set all frozen in the visibility map. And the red line is the patch and the purple line is master. And that sort of jump that you see in master is an aggressive vacuum. So this is when there's one aggressive vacuum, this benchmark runs for a few hours and has one aggressive vacuum. And these are all the auto vacuums, so many, many small auto vacuums. So it's smoother and they take less time, each one. And in this case, actually, the total time spent vacuuming was lower because what we said earlier about the quiescence and how, once a page is evicted and then you have to read it back in and write out, that you get write amplification, not doing that saves you some I/O. So you can see the total time spent vacuuming is less. And that seemed great, but there was a really big problem. And so that I said was a hot tail workload where the end of it's like you're inserting and updating data. And, but the actual, the case that we hear about people having their system fall over is they have a giant insert-only table that is just like they're adding data, terabytes of data. Suddenly they have an aggressive vacuum and it's the end of the world, right? So for my distribution, the way that I built it was its updates and deletes are page modifications and inserts are not. So even though an insert changes the page LSN, you're an inserted tuple, if you're not, like an update and delete is going to unfreeze a tuple. So those are page modifications. So there are no modification intervals for an insert-only table. So distribution's empty. Well, it seems like, you just freeze everything then. When the distribution's empty, you don't have updates and deletes, so you freeze everything. But the problem is sometimes people modify insert-only tables, or they have an insert-mostly table, right? Like you might want to go and tamper with some old data in your audit table, or, anyway, you might want to modify a few things. And suddenly you have a distribution that represents a very small amount of your data access pattern, but is all the data that you have, which is just from those updates and deletes. So you're missing all of the pages that weren't modified, all those all visible but not frozen pages. So what I was thinking was, you're not missing them, they exist. You just don't know about them because you didn't record durations for them. So what if when we update or delete a page, when we set a page all visible, we add its LSN to, let's just say, a list. We're going to keep all the LSNs. And then when you update or delete something on that page and you have to set it not all visible, you remove that LSN from the list, right? So now at a given time, I have the current transaction ID. I want to calculate how old all my data is. All my all visible but not all frozen data, I want to know how old it is. I have all those LSNs. I'm just going to calculate that based on the current transaction ID. So that's like totally doable. It's something you could do. Obviously, you wouldn't store every LSN. You would use some sort of structure like a histogram, right? But previously, the distribution I showed you, there's a lot of ways it used durations, right? These are absolute LSNs, which is like a monotonically increasing number. And as far as I could come up with, there wasn't a cool sort of distribution that easily represented that. I needed to use like sort of a bog standard histogram. For the other distributions, I was able to use things like assume they approximate a normal distribution, and then I could store 3 scalar numbers and to have the mean and the sum of squares and whatever, and use that to be able to calculate the areas on the probability distribution without having to store a bunch of non-scalar data. In this case, I needed to have, like, as far as I could tell, I'm sure, maybe someone else could come up with ways to solve this problem, but I needed actual histograms. And then this data was per table in the shared memory stat system. And that in the shared memory stat system, when I needed to update it when I was doing an update or delete, and that was being done in back-end local memory, and then that gets flushed out to the shared memory stat system when the transaction commits. So that meant that what if the binning changed? What if something about the histogram and shared memory changed while my transaction was going on? Well, now, before I commit my transaction, I have to go and figure out how to rebin the data from my backend local memory into the shared memory histogram, and all of that's like solvable problems, right? But it's a lot of code. And the actual distribution I showed you earlier was actually much more complicated too, because we only have one page LSN. So you actually there are operations other than update and delete that change the LSN. Setting hint bits, there's lots of operations that change the LSN. So if you had two, you could know the unmodified duration. But with one, there were lots of ways that you could end up not having the right picture. So I did multiple distributions and convoluted them to actually come up with that distribution. And then I needed to combine that with the histograms. So it was a lot of code. And the issue was it was all very tailored to my small thing that I'm trying to fix, this one freezing thing, this one place. And it wasn't clear how I could reuse that infrastructure for other projects. The shared memory stat system is also, like, we already know it has the problem of it doesn't work, after a failover, you won't have the stats, which is already an issue for auto vacuum triggering and things like that. So there were so many problems that I would have to fix to have even the basic infrastructure, to have even the start of this project even working. And at that point, like, there were lots of even additional problems. So, and I can go into more detail about them if you meet me in the hallway track, but I have only a couple minutes left. So I sort of started to think, like, I need to think about the problem completely differently. And instead of trying to exactly predict when I should freeze a page, let's just, like, split aggressive vacuum up into smaller pieces and scan the pages sooner. And scan those all visible pages during normal vacuums, small pieces of them. The issue there is that it's also wasted work if you don't end up freezing them. So Robert had the idea to essentially do something really simple, which is stop freezing, or stop eagerly scanning all visible pages if you can't freeze them. So, like, we'll scan a few all visible pages, and then if we didn't freeze them, we'll stop scanning more of them. And this only required tracking information within one vacuum with a few counters, no extra infrastructure, no new APIs. And as far as I know, this is the only place right now in Postgres where we do this kind of, like, stop doing the bad if it's not working, So I think it was really cool in the end that we came up with something. But I think that the lessons that I learned from this was that if you saw the progression of the presentation, the question that I was asking changed a lot. If I'd figured out what problem I wanted to solve at the beginning, I would have saved a lot of time. But you know how that is. And then the other thing is that most of the time when you're writing Postgres code, people tell you to try to break the problem down into smaller pieces and break the solution down into smaller pieces. And in this case, as an example, we tried to basically, there were different ways that we tried to break the problem down, and none of them really worked. So I think, like, there are situations where you can't actually break the problem down any further. And the example was that Robert had the idea of, what if we, for an insert-only table, the first time we vacuum a page, we freeze it. And that way, the maximum amount of failure we'll have is one frozen page. Like, we'll have frozen a page one extra time, right? And that ended up not working, because if you have an ETL workload, automatically you will have regressed all ETL workloads, because every single page that you froze will immediately be unfrozen when you update it. So there was all these little catches where it's like, okay, we can find a simple solution, but actually it completely regresses this other workload. So I think like sometimes you have to admit defeat in attempting to simplify your problem. In the future, I think we should just not do freezing in vacuum. Yeah. Okay. Anyway, adaptive algorithms are hard, but we should probably do them. And thanks to Andres and Robert. And my employer let me work on this, even though I failed for 2 years at it. So you should answer their survey and tell them if you like that. Yeah, that's all.